Now, before we consider the table on slide 43, I just want to remind you that when we're thinking about addresses, and the example that's on the slide here is a logical address, what we should keep in mind is that we're thinking about an address which has two components to it. So it has a page number and it also has a page offset as well. So we'll see this concept in a little bit more detail when we get on to slide 43. And we see the table which shows the mapping of logical addresses to physical addresses. So the table that we can see in slide 43 is intended to be reviewed with the content of figure 11 on slides 39. So I'll Alt-Tab back and forth between the two slides, and I think that's what you should try to do as well as we discuss this. So let's consider table 1, and what table 1 shows us is the entire set of mapping of logical to physical addresses for the process that is shown in figure 11. So it's all of the logical addresses mapped to the physical addresses that we can see here. So let's consider how that's done. You can see that the first three columns are related to the physical, to the logical addresses, and you can see that we have logical addresses for the process given first of all in decimal numbers and then in binary numbers. So you remember that when we were thinking about this diagram here, we had a bunch of logical addresses which went from 0 through to 15, and they had to be mapped over here to the corresponding physical addresses which would be in each of the frames that were stored in the page table. Okay, so that's the content of this column here, and you can see that where we have, for example, logical address 0, well, when we write that out as a binary number, we write it out as a 4-digit number. So that 0 becomes 0000. And if, for example, we're considering the logical address 1, well, in its binary representation it is 0001, and so on and so forth for all of the logical addresses. What we can also see as well is that there's a column for the MMU mapping. We'll come back to that in a second, but this is the arithmetical transformation that is carried out by the memory management unit as it converts logical addresses into correct physical addresses. The final two columns are set aside for the physical address, which is given first of all in a decimal format and then is also given in its binary representation as well. So let's consider logical address 0. So in the diagram you'll see that logical address 0 is here. Its content is the machine code instruction A, and if we look at the page table we can see that page 0 is mapped to frame 5. So there's frame 5 there, and there is the content of the machine code instruction A, and you can see that the mapping is from logical address 0 to physical address 20, like so. Alright, so that's the conversion that we have to carry out from 0 through to 20. So if I hop back to our slideshow and go back to the table, you can see there is the logical address 0 stored inside page 0, and you can see that the binary representation of it is 000. So that's equal to decimal 0, and that seems, I think, pretty straightforward. But it also not only represents the integer 0, but it also represents the page and the offset number. So what I'm going to do is just split this number into two parts. The first part is the page number, and the second part, this bit here, is the offset number. So the page number for this address is equal to 0, and the offset is equal to 0 as well. Okay, so we'll just park that for the moment, and then what we'll do is we'll imagine that the logical address in its binary form is input into the memory management unit and is arithmetically transformed. So the transformation is really quite simple. What the memory management unit does is it looks up the page table for the page table entry for the page 0, and it sees that it's mapped to frame 5. So you can see that there, that's quite clear. 0 is mapped to frame 5. So with the frame number, what it does is it multiplies 5, the frame number, by 4, which is the size of frames in the system and also the size of pages, and it adds that to the second component of the logical address, which is the offset inside the page stroke frame. So 5 times 4 gives us 20. Add on the 0 and that will give us 20 also, and the mapping is thereby achieved, and we can see that logical address 0 is mapped to physical address 20. Now of course this is the decimal representation of it, so if we write 20 out as a binary number, then we get 10100, which when considered by itself without any changes is equal to 20, but also simultaneously represents page, or rather frame 5, f is equal to 5, so that's this number here, 101, which is the binary representation of 5, and then the offset d is equal to 0, like so. So this is quite a nice trick. Our binary numbers are representing two things simultaneously. They're representing a logical address, first of all as an integer, as 0, but they're also representing the page number and the offset, d, and then when the translation has taken place, the transformed physical address represents the physical address as an integer, but also simultaneously represents it as a frame and an offset. Now what you may have noticed is that the offset doesn't change, or the offset component in the physical and the logical address doesn't change. It is only the page number that gets transformed into the frame number. Okay, so let's look at that again, and this time we'll do the next one, which is logical address 1. Okay, so logical address 1 maps, according to the picture that we have here, there's logical address okay, so there's logical address 1. Its content is B. It's in page 0. Page 0 is mapped to frame 5, and when we look up frame 5 and we look for B, you can see that it is stored in memory address 21. So the mapping that we're looking to achieve here is from logical address 1 to physical address 21. Okay, so that's how it's represented pictorially, and then if we go back to our page table and we look at the mappings that are available to us, you'll see that we have logical address 1 in its decimal format, which can be written as 0001, which can then not only represent the integer 1, but it can also represent the page number and the offset value. So if I split that into two components, we can see that we're dealing with page 0, offset 1, and then if we look at the page table, well, what we should be able to observe is that page 0 is stored in frame 5. And when we do that multiplication, which is 5 multiplied by 4, that gives us 20, plus then the offset value, which is 1, well, that will give us 21. So when we write that out as a binary number, well, 21 is 10101, but it is also simultaneously representing two components. The first component, 101, which is frame 5, and then the offset, which is 0001. So if I tab back, you can see that the offset is always worked out by counting within the page or the frame. So there's offset 0, 1, 2, and 3. And there is offset 0, 1, 2, and 3. So each frame has an offset, which is 0, 1, 2, 3. Each page has an offset. So for example, if I was looking at F, the offset value for that would be 1, because we're counting 0, 1, 2, 3, like so. Okay, let's try a slightly different one. So I'll just tidy up the diagram, and we'll do a different logical address, and what we'll do is we'll look at one which is in a different page. So I'll highlight the logical address 5, and if I go back to my diagram, you'll see that the logical address 5 is stored in page 1. Okay, so we look up page 1 in the page table, and we see that it's mapped to frame 6. Frame 6 is down here, and you can see that the contents of memory address, logical address 5 are F, and when we go and look down here, we'll see that this is memory address 25. Okay, so the mapping that we're looking to achieve is logical address 5 mapped to physical address 25. So I'll tab back to my table. There's our logical address 5. When we write that out as a binary number, it is 0101. So that can be read as the binary integer for 5, but also as well it can be simultaneously read by splitting it into two components as page 1 offset 1. Okay, so page 1 offset 1. So what we then do is we go back to the page table and we say, okay, where is page 1 stored? Well, page 1 is stored in frame 6, and if we go back and we look at our page table, or look at the MMU mapping, the transformation, well, that transformation will be 6, which is the frame number, multiplied by the size of the frames stroke pages, and adding on the offset value, which is 1. So when we do that, we get 6 times 4, which is 24, and that gives us a physical address of 25, which is what we're looking for. And then when we consider 25 written as a binary number, we can see that if we break it into two components, like so, we will observe that this reads as frame 6, which is the 3-digit binary number on the left hand side, highlighted in yellow, and then the offset value is D, which is equal to 1. And right enough, if we just tab back here, here's frame 6, which is in our system 101. And then if we look at F, well, if we're counting offset 0, 1, 2, 3, then we can see there is the value of D. So that's D there, and this is the frame number here, which is 110, frame 6. So I'll do one more just for the sake of absolute convenience, and we'll do, I think, memory address 12. So I'll just tidy up this diagram and we'll give it a lash. So here is our logical address. We'll do 13. Okay, 13 is not so bad. So let's go back to this picture here. And again, we just scrub up the diagram and we highlight our logical address, which is 13. We can see that the content of 13 is n, that it belongs inside page 3. When we go to the page table, which is stored inside the memory management unit, we can see that page 3 maps to frame 2. There's frame 2 there, and we can see that the starting address of frame 2 is 8, and that when we consider the offset value for n, which is 13 in its logical form, we'll see that the offset value is 1. Okay, so we're looking to achieve a mapping which is between the logical address 13, and we want to map that to the physical address 9. Okay, so we go back to our table, which represents all the possible mappings that can be achieved for this process. And as we already noted, we start off with 13, this is our logical address. We write that out as a binary number. So 1101 is the binary representation of the integer 13. If we split that into 2, you can see that the first 2 digits are for are 11, which represents 3, and the offset D is 01. Okay, so when we go to our page table, we can observe that page 3 is stored in frame 2, and then we do our multiplication. 2 multiplied by the page stroke frame size and adding on 1 will give us 9, which is our physical address. That's exactly what we expect. There's 8, and there's the content that we're interested in, which is 9, like so. So when we write that out as a binary number, we can write it out as 01001. We can then split it into its 2 components, like so, and the first component, which is 010, is equal to 2, so the frame value is 2, and then the offset, which is represented by D, is 01, which is 1. So that makes sense. There's frame 2, and there is our offset 01, like so. So that's really quite a powerful mechanism for doing memory management. The transformation that takes place here inside the MMU is optimized to be done as quickly as possible. So all of these transformations, this isn't, I suppose, accurate, but it is truthful in some sense. All of these can be done very, very, very quickly. So the memory management unit does not run any slower than the main memory, and that's really quite important when we think about the overall efficiency of the system. So let's summarize all of that, and the slide in slide 44 shows you what the issues are, and I guess some kind of key points that would arise here is that pages and frames are the same size. A program gets broken up into whatever number of pages it requires in order to satisfy its logical address space, and then basically when you want to run a program, you have to find a similar number of free frames and you copy the pages into the frames. You need a table, a page table, to map the logical to the physical addresses, and the very, very important benefit is that you eliminate external fragmentation. So you don't have the problem that we saw earlier on with contiguous allocation, where you have a situation where there may be enough memory in the system, but because it's not all bundled together, you don't have that issue that you then can't load the process. All you need to run a process is a certain number of frames, and as long as those frames are available anywhere in main memory, then this system will work particularly well. You'll see also as well that there are some other data structures that need to be taken account of. So for example, we need, and this is the kernel that would be doing this, it would need a data structure called the free frame list. So in this example here, you can see that you've got a new process. These are its logical pages here. And before this process can execute, it has to be loaded into main memory. So what the kernel does is it comes along and it looks at the available free frames. So we can see that this process needs 4 pages to be loaded in. There are 5 frames available. So what then happens is that the process finds that its pages are copied in to available frames. So frame page 0 goes to frame 14. Okay, so there's frame 14 there. Page 1 goes to 13, which is up here. Page 2 goes to frame 18, and page 3 goes to frame 20. So again, the important thing is these frames are not contiguous. As long as we have 4 frames available in main memory, then this process can run. Okay, so that's the kind of key insight, and we also get, of course, protection and relocation using this system, because it incorporates the previous mechanisms by default of its translation mechanism.